all GNSS systems produce such type of satellite signals, and these signals generically contain 3 layers. And in the first layer, the navigation message file is stored, and in the second and third layers, the observation data files observation data are stored. So the GNSS signals have omnidirectional structure. This means that the antennas at the user side capture the signals without directing the antenna to a certain location, to a certain satellite direction. So the antennas can easily identify from which satellite the signals come. So, and after obtaining the satellites, capturing the satellites by the satellite signals by the antennas, and then after capturing at the receiver, these data will be stored in 2 important files. The first file is the navigation message file, and the second file is the observation data file. In this lecture, we will concentrate on the navigation message file. So one such navigation message file is the GPS broadcast system. So this is, for example, the human readable format, ASCII format, RINEX file. So the description of the RINEX file can be found within this week's documents. So RINEX here means receiver independent exchange format. Each receiver vendor or each company, for example, Leica, Trimble, produces its own data format, and these data formats are mostly binary formats and cannot be read by the humans easily. That's why we need these formats, these binary formats, to be converted to a suitable format, which is called as RINEX. So the RINEX is an accepted format by the countries. So each satellite or each antenna or receiver producer will generate always the documents, or will convert the document, the observation or navigation file to RINEX file. So you see here an example obtained at a site in Ankara. So, and the structure, as you can see, is can be read by the human beings. So we can then make some computations by using this file. So the description, as said, the detailed description can be found in the RINEX version document. So we don't want to go into the details, but the broadcast file, this GPS satellite orbital information is stored in this file, and you see 2 important blocks. So the first block, as you see, is here the header block, and some necessary details are given here, and the remaining, the second block is the satellite coordinates and satellite necessary information block. So you see, for example, the GPS satellite 101 is given here, the block. You see there are 8 lines, 8 rows, and 4, you can identify 4 main columns. So if you go further down to the file, you can see the GPS number 2, satellite number 3, and etc. So you can find at a certain time. For example, GPS 2 satellite is given for 2019, the first month and the first day. So this means 1st of January in 2019 at midnight. You can see the satellite's orbital parameters. So the GPS satellite's coordinates are given at every 2 hours. So, for example, this data, this navigation data is for the 1st of January 2019. So that's why you can see, okay, for the entire day within 2 hours interval, all satellites orbital information. So within this 8 lines, 8 lines of block here, you can see each satellite, you can compute each satellite, okay, three-dimensional coordinates in an Earth-centered, Earth-fixed coordinate system. So let's now go on what these okay, locations in the file mean. So this navigation file for the GPS is also denoted as the broadcast file. So there are some descriptions in the header. For example, the Rhinex version is 303, for example, and the system for the satellite coordinates is given for GPS system. And now you can see there are some necessary information included in the header. So let's go into the details what these mean. For example, here the coefficients alpha and beta coefficients denote the ionospheric correction. So the ionospheric correction is necessary for making our measurements for correcting our measurements due to the ionospheric effect. So these corrections can be done within meter accuracy. So for higher accurate positioning, this way is not used. So normally we use the reduction or the eliminating of the ionosphere. So there are 8 parameters, as you see, 4 alphas, 4 betas, and these 8 parameters refer to the locations, the zenith direction. So this means if you want to determine the ionospheric correction at a certain azimuth and elevation angle, so you need to make some extra computations by using a model. And these model coefficients are for Klobuchar model. And for each station and for each day, these coefficients may change. So that's why the user can also be can use this 8 parameter Klobuchar model for the determination of the ionospheric corrections. As said, so we want to reiterate, we want to say it again that these corrections can only be applied for meter level positioning, not millimeter or centimeter level positioning. So in the second line, so here you see the correction from the GPS system time to the universal time coordinated. And at the third line, you see the leap seconds. So we don't want to go into the details. If you would like to have the information, extra information, please refer to the Rhinex document available in the repository of this week. So GPS system uses so all GPS satellites use the atomic time. So as you know, the international atomic time is a constant time that does not change within time. So and this time is shifted by 19 minutes, as you can see by for GPS and Galileo times. So it is because the origin for the GPS system begins at January 6th of 1980. And as you see here, we refer to in daily life universal time coordinated, and it is a stair-like structure you can see here. But universal time is a continuous curve, and the universal time coordinated is a civil system time. It does not change with time. For example, for a certain period of time, the same time system is valid, but in UT1, as you see, it changes steadily within time. So for that reason, we introduced universal time coordinated. So, but you don't need to know the details, but you only need to know that the GPS and all other GNSS systems use the atomic times, and the relation between these time systems. So, for example, the GPS system time to the universal time coordinated is given by a polynomial. So then this polynomial is also included in Rhinex files, in navigation files. So let's go on with the blocks. Uh, blocks of the data file, so navigation file. So here you see in the first, second, third, fourth, and fifth column. So in the first column includes the satellite number. So G denotes the GPS system. So we will see later, or you can also refer to Rhinex document, and you will see, if you see there R, so this means Russian system, and this is GLONASS satellite. If you see E, this denotes European system, this means Galileo satellite. Or if you see C, this is Chinese system, and this denotes Beidou, etc. So for the convention, so every country in the world uses the same convention, and this convention for the GNSS positioning is Rhinex. And in the Rhinex, G means GPS. The GPS, satellite number 1 here is denoted, and within this block, as you see in 8 lines, the necessary information for the computation of the coordinates, of course, this the satellite's orbital information is stored. What about the second column? In the second column, you can see the time of the clock. So this clock is GPS time, be aware. So the GPS system time. So in the year, month, day, hour, minute, and seconds, structure. So in the third and fourth and fifth lines, you can see the satellite's behavior. So the satellite, for example, each GNSS systems or GNSS satellites, or for this case, each GPS satellite has its own clock system, and this clock is not synchronous with the GPS system times. This satellite clock is a little bit shifted and shows some drift. So in this, as you can see, it is shifted by nearly 0.1 microsecond, for example, 0.13 microsecond, and you see the drift of the satellite, and the drift is so small, as you see, 6 times 10 to minus 12. So this means that after nearly 1 minute, so if you multiply this by 60, and in 60, this will result in nearly 4 times 10 to minus 10. So 10 to minus 10 means 0.4 nanoseconds. So this satellite will show the time in reference to the GPS time, after 60 seconds, 0.4, nearly 0.4 nanoseconds, less value. So, and in the third component, you see the acceleration. So this is the drift, as you see, second per second. And the acceleration, as you see, of the satellite is denoted as 0, because this value is so small that this is not included in the correction system. So in short, we can say this information in included in the first line, and the third, fourth, and fifth column is about the satellite clock in reference to the GPS system time. So it's an important important line here. So in the second clock, so you can omit the first column, and in the second, third, and fourth columns, you see the some Kepler elements available. So the satellites change their location within time. So, for example, these the satellites distance from the center may also change due to some effects, so some accelerations. So that's why you need to model this acceleration. For example, this is the coefficient in the r direction, so the direction between the satellite and the Earth center of mass, and this direction can change within certain time, and this is the amplitude given here in the second column. This is the amplitude which will be multiplied. You will see later with an angles, a sine or cosine value. So, for example, this is C, an amplitude value for R, and for the sine, for sine component. So now delta n denotes that the satellites, the mean anomaly, so the anomaly change within a certain time, and delta n is denoted here as the mean motion, the deviation from the mean motion, and as you see, it is also brought as a correction to our formulation. So we will see how these formulations are computed. So M0, as you can recall, M is denoted as the mean anomaly at a certain time. The certain time is here, as you see. It is 31 December of 2018 at 18 o'clock. So the M0 value is included here. So this is the mean anomaly. So in the third line, you see there are so as we stated that this within time there is some change in the r direction. So we also have in the angular direction. So for example, these are the coefficients for the cosine term in the u angle. So these are in radians. What does u angle mean? So you can see in the document attached into this week's repository. So one of the Kepler elements is the eccentricity of the orbit. It is included here, third line and the second column, and you see this was in the u angle amplitude in cosine term, and so you see here in the sine term. So this is in the third column. So now in the fourth column, you see here the square root of the semi-major axis length. So this is denoted by capital A. So you recall in our lectures we denoted by this term by lowercase a. So here is uppercase A. So if you take the square of this term, you will see the distance, the distance from the center of the Earth to the perigee direction. So this is the semi-minor semi-major axis of the ellipse we used. So this is given in square root format. So what about the fourth line? So this is the time of ephemeris in GPS weeks. So every GPS weeks begins at Sunday midnight and ends again next week Sunday midnight. So this means 7 days, and if you multiply 7 days by uh, each day's interval in seconds, so this means 86,400. So you see the minimum and maximum values of a GPS week in seconds. So you see here this value is around 151,000, 51,200, so around. So uh, so this is okay, as you see, can take values up to 700,000 seconds. This is the limit for if you multiply the 86,400 by 7, you can find the limit value. So the change again, not only in U angle, not only in R direction, so there is also change in the inclination of the orbit. So this is the amplitude of inclination in the cosinus cosine term, and you see in the fourth, as you see in the sine term, and omega 0 here in the third column denotes here the the right ascension value. So this does not denote here in GPS the right ascension at a reference time. Okay, this is the longitude. Okay, the longitude of the ascending point. So we defined this omega as the right ascension of the uh, ascending node. So but in GPS we generate not space fixed coordinates, we produce earth centered coordinates. That's why this omega 0 is referred to the longitude. So these angles will refer not to the we will not refer to the vernal equinox. This omega 0 will refer to the Greenwich meridian. So in the fifth line, you see this is the I0 radians at a certain time. So we mean at this reference time, which is given in the GPS system time, weekly GPS time. So the knots or the zeros denote this very time, and I naught or I0 denotes here the inclination of the orbit at that time. So as you can see, we need some corrections. So we have introduced in the previous slide CIC and CIS. We will then make some computations for a certain time, for a later time, for example. I0 at a certain reference time, it denotes the inclination of the orbit. So you have seen that CRS was already introduced. So this is the change of the direction in the in the R. So R means the center of Earth to the satellite itself. So this change with time with a harmonic function. So these are the coefficients, or these are the amplitudes of the harmonic function. So CRC given here in the second line. So lowercase omega now denotes argument of Perigee. So it does not change with time. So it's like E. So within this time, at least. So the GPS orbital information will be disseminated every 2 hours. So this block of information, as you see, this block of orbital information will be valid for 2 hours. After 2 hours, a new block will be emitted to the user, and he or she can use this new information with new values. Okay, be aware that the GPS broadcast file, okay, for each satellite will be updated every 2 hours. So there is a change in the longitude of the ascending node, omega dot, and so this means that the ascending node will not stay the same; it changes with time. Omega dot means the rate of the change within time. Now we are in the sixth row, sixth line. So, and this one I dot means that this is the change of the inclination within time. So it is a function of time again. The inclination is not constant through this 2-hour interval. It changes also with time. So we can omit the second information, and the third information, as you see, is the GPS week. We said that each GPS week can be divided into seconds. So beginning from 0 up to, if you multiply with 86,400 times 7, so this is nearly 604,800 seconds, and this is denoted as 1 GPS week and 2 GPS week and 3 GPS weeks, and etc. As you see, since the initiation of the GPS, these number of weeks are counted, and now we are at the 2034 GPS week. So fourth column can also be omitted again. Now, so you see in the first column here the space vehicle accuracy. So the accuracy of this orbit is given in all three components, X, Y, and Z, Earth-centered, Earth-fixed coordinate system. So the norm of this accuracy is around 2 meters. So you don't expect that this orbital information is low accuracy. So it is not high accuracy. You cannot expect a centimeter or decimeter values. So, but these instantaneous every 2-hour valid GPS satellite coordinates can be obtained by for this satellite, for example, 2-meter accuracy. So we can omit the second and now the third and the fourth components. These are not necessary. So now and this information is transmitted to the user at this GPS time in a second. So this is also included in the file. So and now by using this block of information, so for example, if we carry out an observation at 19 o'clock, so we can use this orbital information, and for example, it is 21 o'clock, for example, you cannot use. You must use the data block belonging to the 20 o'clock, beginning from 20 o'clock. So that's why you can use this block only for 2 hours. So how will we use this block for computation? So there is in the repository of this week a so-called interface specification document for GPS system, and every GNSS system has its own interface specification or interface control document. So you can use these documents to make some computations, and if you are a vendor, if you are a receiver producer or antenna producer, you can use how to interpret the signals, how you can embed the recognition of the signals into your software, so etc. But for geodesy user, we need to make some computations by using these elements, and these are given in this document, in this interface specification document. As you see, these are constant. Nu is the gravitational constant. So this is the standard for GPS system. So this is the Earth rotation rate, the second information, and the third information. As you recall, the semi-major axis is given in square root form, and if you take the square of this, you can obtain the semi-major axis itself. So the mean motion can be computed by using nu divided by a to cube. If you take the square root, you can get the computed mean motion. And as you recall, this delta n is introduced, is given in the block, and if you add n0 by this delta n, you get the mean motion of your satellite, and you can then compute the mean anomaly. As you recall, m0 or m0 is also given in the file, so you can, for any time, you can compute mk. So how mk is computed? It is used by tk, and tk is the time of the observation, and so this is the TOA is the time of Ephemeris reference epoch. So for example, the time of Ephemeris at the beginning of Sunday at midnight, for example, from Saturday to Sunday midnight, it begins with O and it ends, okay, next week, 1 week later. So the maximum value will be 604,800 seconds. So this TOAE denotes this, okay, seconds from the beginning of the GPS week to the end of the GPS week, okay? So, and the time of ephemeris denotes here TOE, and T is our observation time in seconds. So we must convert our observation time to the GPS time in seconds, sorry. So as you can see, we can then compute the MK, and by using MK, we can get the eccentric anomaly E. So you are familiar with this, and this is the Kepler's equation. And by making some iteration, you can obtain EK. And after getting EK, you can get also the true anomaly nu K. So now if you proceed, so by using nu K, so if you add omega, argument omega, this is the argument of Perigee, and you can obtain an auxiliary value which is called argument of latitude. So you remember we had some amplitudes. Yeah, so there are 6 amplitudes included in the file, in the broadcast file. So by using those amplitudes, we can make some corrections, okay? Some harmonic, by using this harmonic equation. So for example, CUS means is for the S sine term, CUC for the cosine term, etc. You can make the argument of latitude. So what does argument of latitude mean? So this means it is the angle, okay? Normally, lowercase omega means the argument of the perigee. If you add the satellite's position angle, so the true anomaly, so you get the argument of the, okay, latitude, or argument of the satellite's position, okay? So in the argument of perigee, or perigee denotes the Earth close point, okay, to the satellite. So if we add nu K, we obtain argument of latitude. So this is auxiliary information for the computation of these terms, these corrections terms. And after that, we can use this, we can get this, okay, corrected argument of latitude UK. And by making the computations, the necessary computations, if you proceed here, you can get the Earth fixed coordinates, so X, Y, and Z coordinates. These are Earth fixed coordinates, not space fixed coordinates. These coordinates, so this system, the coordinate system, rotates with the Earth itself. So its X-axis directs towards the Greenwich reference meridian. So that's why these in the term it is included the Earth's rotation rate. So omega dot E, so here denotes the Earth's rotation rate. So by using this, you can easily compute a satellite's position for any given time. So as said before, we want to make this again. We want to say that again, that the interval for the GPS satellites, for GPS orbital information, is for 2 hours. Okay, so every 2 hours this satellite information will be renewed, will be recalculated for the system maintenance, and will be uploaded to the satellite, and the satellite will then send to the receivers. In this way, you can compute the satellite's position with meter accuracy, and by using these coordinates, you can use satellite's position for the position determination. So this is now for GPS. In the next lecture, we don't go into the detail, but we will see for the GLONASS system.